Alrighty, CNT125, Chapter 8, we're on the section on VLANs. Now, right before this slide, I have the switch review slides copied in again, just in case they're handy to flip through to get ready to talk about VLANs. Alright, VLANs. If we remember from the very beginning of the chapter, subnets were a way we could segment the network at layer 3. VLANs are a way we can segment a network at layer 2. So we're now going to talk about VLANs. VLAN is a virtual LAN. It's a group of ports on a switch that we group together for like traffic, either the same department or the same type of device like phones or access points or computers in a certain department or a certain room or a certain floor of a building. These virtual groupings can be on one switch or can actually be across multiple switches. I could have a phone VLAN and it might be the handful of ports on the floor 1 switch that has phones in and a handful of ports on the floor 2 switch that have phones in. I could group those together even though they're on separate switches into a phone VLAN. The same thing would be true for maybe access points for a wireless VLAN, and the same thing would be true maybe for certain access points that we have for visitors. We might put them in their own VLAN for security purposes. So it's a virtual LAN where I don't have physical boundaries. I can do logical boundaries to kind of rope them together. So logically separate networks within a network, group of ports in, these ports then kind of come together into their own, we make them their own broadcast domain, their own type of traffic, if you will. The chapter didn't mention this, but I'm going to mention it to you. We can actually assign VLANs two different ways. We're going to do a lot of our work statically. We're going to take certain ports on the switch and put them into a VLAN. When we do that, when we take certain ports on a switch and put it into a VLAN, that's port-centric VLANs or static VLANs. The other way we could assign VLANs is dynamically. I could actually have MAC addresses, a certain MAC address, get put into a certain VLAN. Example, if somebody plugs an IP phone in, we could have that MAC address programmed into a server that when that phone plugs in and turns on, that MAC address goes through the network and hits the server, and the server goes, oh, that MAC address, that's a phone that belongs in the phone VLAN, and it literally assigns it to that VLAN, that phone VLAN dynamically. But it does require a server to do so. Okay. Our focus on labs and in the lab room will be on static, but the dynamic VLANs do exist if you have a server to support that. Anyway we do this, each VLAN is going to be its own broadcast domain, which is the whole point of doing this. So they use a picture like this showing, hey, I can have computers scattered across multiple floors, multiple wings of a building that all need to be in the same VLAN. Same thing here. I have multiple computers and devices across multiple floors that need to be in the same VLAN. And I don't have to, it's not a physical boundary, it's more of a logical boundary that I do this. Well, let's dig into this just a little bit further. Earlier on, we had the example where we had, multiple floors of building, and we allocated a subnet to each floor, and a router connected that floor over to another main router in the building. That is one way to do this, and I have now smaller networks with a larger one. But this could be either cost prohibitive, or it might not physically be possible because my routers may not have that many ports on. Routers a lot of times don't have that many ports on. Sometimes it's only 2, and in and out, if you will. So that might not be very possible, which brings us back to this. I might use a switched environment and group similar devices together into a VLAN, whether it be certain computers in a certain department, or all my computers into one VLAN, all my phones into a different VLAN, all my wireless access points into a different VLAN. Which brings me to this example. Mr. Brown puts this in here to try to get you to start seeing where I might use this. So if I have this type of environment, where I have desktop users, if you will, that could be employees, it could be bosses, etc. We have IP phones and we have access points for wireless users. A lot of networks have this. Well, if they're all together in the same switch, that's a bit of a security concern, because all that traffic is mingling through the switch here, and in many cases, you could run Wireshark here and start picking up packets of data from the phone or packets of data from the wireless users and potentially get compromisable information. Now, We're not doing that ethically in our lab room. We are not doing that. But in reality, that could occur. So one way to prevent that is if I do separate these out, separate switches with a router to interconnect them. Now the wired users are in their own network, own subnet. IP phones are in their own network, own subnet. Wireless users are in their own network, their own subnet, and the router is going to keep that traffic separate. So if I tried to Wireshark, over here run Wireshark and capture IP phone traffic, I wouldn't be able to do it now. So mission accomplished. However, I just added more cost by adding more switches, and I added more ports on my router that I may not have. I may not have that many ports. I can buy them, but sometimes they can be pretty pricey as well. So a solution that often gets used is just this. On my switch, I create VLANs for each of these different populations. A VLAN for desktop users, a VLAN for phones, a VLAN for wireless users. And on the switch now, segments those apart at layer 2, and we'll pass the data to the router, and the router can be the decider of, can this group talk to this group, can this group talk to this group? And many times on the router you write rules to say no, they cannot. No, they cannot. Those two populations don't need to talk to each other. They should not talk to each other. And that will keep them separated at layer 2 here with VLANs, and the router would keep them separated at layer 3 by subnets, if you will. This arrangement gets used in a lot of networks where I can separate those populations out with adding minimal devices, just some configuration. So the reasons I might use VLANs, I might be able to identify groups for priority handling. In an environment like this, I might give these workers priority of data over the wireless, maybe visitors. Okay. I might be able to isolate connections with heavier unpredictable traffic patterns. Yeah. Especially this wireless over here. They're isolated. I might isolate groups that rely on legacy protocols. Again, I might have a network here using, let's say I have a network over here using older point-of-sale machines. Again, I could keep them separated. Separate groups users who need special security or network functions, yes. I could actually write rules here on the router called access lists that will filter these wireless users and maybe only let them use web traffic, and that's it. Web and DNS traffic, if you will. No other traffic through there to, hey, you just need to browse. You're able to browse, and that's pretty much it. I can do it for temporary networks, and I can also reduce my costs of networking equipment as we showed. So some benefits of VLANs, they are flexible. I can configure my switch to accommodate almost any arrangement I need to on these ports. I can use almost any end node type. PC, IP phone, wireless access point, IP camera, etc. I do have less physical equipment, and I do have broadcast control and security control by adding these VLANs. Downside, I do have an additional config that I need to get right. If I get it wrong, I could be isolating parts of the network or causing connectivity issues for parts of my network. I may need layer 3 device to allow this inter-VLAN. I might need that router or layer 3 switch at the top up here, let me go back up here again, to allow this inter-VLAN or control the inter-VLAN, allow certain traffic but not other. This population talk to this population but not the other. So I would need to worry about that. And it is prone to VLAN hopping. This is not foolproof. It is prone to its own type of security attacks, if you will. So to do this, I'm typically dealing with a managed switch. An unmanaged switch is usually not capable of doing VLANs. So on a managed switch, I'm either consoling with command line, like we would be doing in our lab room, or browsing with a web-based management GUI, browsing in to configure. Normally on devices you do some initial configuration to command line, and then after that you can typically browse in and do some management after the fact that way. And I'm going to break my traffic at layer 2 into different VLANs. So I'm creating a broadcast domain for each of the VLANs. So on a switch like so, I could grab a couple ports and put it into this VLAN. I could grab this port and put in this VLAN, these ports here and put in this VLAN, and so forth. I can go through and start grabbing ports and putting them into specific VLANs. And now, when I have the switch here with this over here in VLAN 1 and this in VLAN 2, those are not going to talk to each other directly. The switch cannot do that. That's where the router would come in to say, yeah, VLAN1 could talk to VLAN2. Or a rule could be written here to say, no, they cannot talk to each other, if those are two different groups of devices that I don't want them talking together. So this type of arrangement, when I do this to allow this inter-VLAN routing, they sometimes call it a router and a stick. This router would have the intelligence to read this and say, yes, I will pass this over to this VLAN for you. But the switch is going to keep them separated and not allow that to occur, which is why we're doing this segmentation at layer 2. So to do this, I need to introduce the idea of what's called frame tagging, or a tag. Frame tagging, I'm going to give you some details here. Frame tagging is from the IEEE 802.1q standard. I'm mentioning that because later on we'll do some configuration. We actually use a command that says .1q for .1q here. Okay, so IEEE 802.1q standard for frame tagging. Whenever a chunk of data is going through a switch and coming through that VLAN, a tag gets added to it. And now it says, hey, this frame of data belongs to this VLAN. I think I have a picture right here for you. So as it comes into the switch port, it's like, oh, this is coming from VLAN 10, if you will. So it slides a tag in there saying it belongs to VLAN 10. Now as it moves from the switch, maybe down the line to try to go out another port, it goes, well, your VLAN 10, I can't pass you out this VLAN 20 port that you're trying to go to. So it's going to identify what VLAN it belongs to, so that a switch or switches know how to handle this to either allow it to go to that VLAN based on that tag, or not to go to that VLAN based on that tag. And I like to think of this VLAN tag as almost a luggage tag. When you go to the airport and put a luggage tag on it saying, hey, this luggage belongs to this person, but this luggage now needs to go through various routes to get to your destination. And anything along the way is going to read that tag and say, okay, it needs to go in this cart. Okay, it needs to go in this plane. Okay, it needs to go in this cart. It needs to go in this cart. It needs to go in this plane. And that keeps reading that tag to get it to its destination. Once it gets to the destination, that tag is kind of useless and you tear it off. Well, the same thing's going to happen with this frame tag. As traffic goes to move from, let's say we do VLAN here, VLAN 1 here, as it comes to move into this switch, it's going to say, hey, you belong to VLAN 1. And as it tries to move it from here to here to here, it gets to this switch and say, oh, VLAN 1, yeah, I can let you go out this port to another VLAN 1 computer or device because you belong to VLAN 1. But as it passes it out, it tears that tag off because it's gotten to that VLAN 1 destination. Okay, and that tagging gets used mainly on these links between the switches, mainly on the links between the switches, and we call that trunking, which leads us to bada bing bada boom, VLAN trunks here. So they mention access port and trunk ports. Yes, so let's mention that quickly. An access port on a switch would be something that a host connects to, a computer, an IP phone, a printer, that sort of thing. That access port would be for a device to get access to the network. Meanwhile, a trunk port is something that we use to connect to another switch or a device like a router. It's there to handle all of this tagged data, all these tagged frames. It's moving across the trunk to another switch and delivers it, and now that switch reads all the tags and starts getting them to the correct ports. So on a switch, I can be grouping ports here for devices to plug into. Those would be access ports. Meanwhile, a port that I'm going to use to connect to another switch would be a trunk port. Now they have it here. You can actually take any port on a switch and make a trunk port. We typically do it on the uplink ports on the end over here. That's typically what we do for trunking, but I can actually make any port a trunk port. And that means it's going to start doing frame tagging and pass traffic from switch to switch while it's tagging the data. Okay, we're going to come back in the next podcast and pick up with this access and trunk port.